Hey everyone, welcome to the Weekly Space Hangout for Friday the 13th, November 2015. I'm Fraser Cain, publisher of Universe Today, and this is going to be your Weekly Space Hangout. We've got a special guest this week, and we'll get to that in a second. And this week is literally all going to be planetary science, except for the X-ray special guest conversation, but mostly planetary science, and that's because Morgan and Sandy are in the same room. Where are you guys?
We're at the Division for Planetary Science Conference in National Harbor, Maryland, which is kind of DC, except not really. So we've been here for a whole week of planetary science conference talks and conference posters and plenary sessions, and our brains are completely on overload, but we're going to spread the love and let you know about what we've been learning about this last week.
Yeah, and normally you guys propose like we're going to have a bunch of stories and we're going to go through them one at a time, but this you've just got like literally a fire hose of planetary science news, and you will fill the this whole episode. We can do 3 of them, and you guys would just keep describing interesting discoveries. So that's awesome. Kimberly Cartier is here as well. Hey, Kimberly.
Hey, Fraser.
And you didn't get to join them in the Planetary Science Conference.
No, I did not go to the DPS meeting, but I'm really jealous because I've been hearing all these fantastic discoveries that they've been talking about all week, and I'm really jealous I'm not there.
Yeah, but if it's planets inside the solar system, you're not interested, right? I mean, if it's got to be outside the solar system, that's when you get really excited about it. And our special guest, we've got Daniel Stern from JPL, who works with the NuSTAR. Daniel, welcome to the Weekly Space Hangout.
Hi there, thank you.
All right, so we're going to take about 20 minutes, 25 minutes, and talk to Daniel, our special guest this week, and then we'll get on to that just litany of planetary science news. And so once again, this is a live show, so you can go ahead and you can ask your questions to Daniel, and I will pass them along as we go. The way you do that is wherever you're watching this episode, you can click to view the Q&A app, and then you'll still be able to watch the video, but now you see a whole big list of questions over on the right-hand side. Put your question in there, vote up the questions that you want us to answer, and that will sort of percolate them to the top, and I'll be able to see and pass them along as we go. But as always, I get the first few questions. So Daniel, for anyone who perhaps isn't aware of what NASA is, JPL, why don't you talk about the NuSTAR project? This is talk about your project.
Yeah, so I am the project scientist for NuSTAR, the Nuclear Spectroscopic Telescope Array, and it's a NASA astrophysics mission. So we mainly look at things outside of the solar system, and what we do is whereas Hubble uses optical light, you might have heard of the Chandra X-ray Observatory studies low-energy X-rays, or Spitzer Space Telescope uses infrared light to study the universe. NuSTAR uses high-energy X-rays, so similar energy X-rays as doctors and dentists use, and we use those X-rays coming from distant objects to study the most powerful, energetic, extreme objects in the universe.
And if I understand correctly, when we think of it's all part of the electromagnetic spectrum, radio, microwave, visible, infrared, all the way up to X-ray, and we sort of imagine these big telescopes to view the visible and stuff. But once you get up to that X-ray spectrum, you've got a more different kind of instrument that's actually detecting this. So what is the kind of the configuration of the NuSTAR? How do you detect these X-rays?
Yeah, so the atmosphere absorbs X-rays coming from the universe, so you have to go into space to do it. X-ray astronomy is just a bit over 50 years old now, since the first observatories. And what NuSTAR does is we actually focus the X-ray light, so we have mirrors, but whereas an optical mirror or a radio dish on the ground reflects the light and you have those parabolas that you're used to, NuSTAR has to do a glancing reflection, so almost like a rock on water. And so the light has to come in almost parallel with the surface of the mirror, bounce off. And so our mirror, rather than being some sort of dish, instead it's kind of a cylinder. And so the light comes in through that cylinder and actually does 2 bounces onto our detectors. And our detectors are these cadmium zinc telluride detectors, but they're solid-state detectors. And it was a challenge to build NuSTAR because these glass, we have what was the number? It was a couple hundred shells of glass in this cylinder. It's about the size of a trash can, and then the focal length of the light is about the length of a school bus, 10 meters long, and so we had to deploy on orbit. I think my profile picture is a picture of NuSTAR in orbit. We have this kind of extreme, funny-looking satellite.
So it sort of had to extend like one of those kind of like old-timey telescopes. When when the ship's captain sort of pops up the telescope and extends it to spy the other pirate ship.
Yes.
Yeah. Okay. Now, for those who aren't aware, what are X-rays really good for? What sort of events are you looking for when you're observing in the X-ray spectrum?
Yeah, so we're very good at studying some of the most extreme things in the universe, like black holes, neutron stars, supernova explosions, galaxy clusters, and we've done a little bit on the Sun and on Jupiter, actually.
There's X-rays coming off Jupiter?
Yeah, that the data is pretty fresh. We haven't. We're still analyzing that.
And so what kind of resolution can you get? I mean, if you're trying to really focus in on, say, the event horizon around a supermassive black hole, how close are you able to get in and see some of these things?
Yeah, so we don't get very sharp pictures. We can't resolve out the regions around the black hole with our imaging. But we're able to, since those X-rays come from so close into the black hole, we're able to start studying things just a couple of Schwarzschild radii out, start trying to map out what the regions are around a black hole. And I should mention that NuSTAR was this change of technology that we're actually focusing the X-ray lights. We have these mirrors and these optics. Previous generation of observatories working these high-energy X-rays were using something called a coated aperture mask, and it was a different technology that basically NuSTAR uses this new technology that was cheaper and bought us about a factor of 100 or a little bit over 100 higher sensitivity. So we've been a real game changer in this field.
And you've been in space now for about 2 years, right?
A bit over 3 years, actually.
A bit over 3 years, okay. Yeah. And so sort of what are some of the sort of major discoveries, some of the big results that you guys have turned up?
Yeah, so it's been a fun ride. We have almost 200 papers out now. But I would say some of the most exciting things we've done is measuring how fast black holes are spinning. And this is a really cool result that we kind of have this picture that, here's my black hole. And so we have a black hole, it's spinning, and it's got a disk of material around it. And there's an inner stable orbit around the black hole that depends on how fast the black hole is spinning. If the black hole is spinning very fast, that inner stable orbit gets pulled in very close to the black hole. If the black hole is not spinning, the inner stable orbit's farther out. And so we're able to measure some of the hot gas and hot material from that inner stable orbit and measure. It gets, if it's very close to the black hole and when the black hole's spinning very fast, the line gets very distorted from relativity, and so we can measure the line profile, figure out how far that material is from the black hole, and figure out how fast the black hole is spinning.
And if I've done a bunch of stories on this, and if I recall that you've seen black holes rotating literally as fast as is possible by the laws of physics, right?
Yeah, we've measured not quite a dozen black hole spins so far, and most of them tend to be like at least 95% of the maximum allowed rate from general relativity.
Like Einstein said, if you guys ever do discover black holes, here's how fast they're allowed to spin. Go ahead and find some. Yeah. And so, I mean, what kind of environment must it be around one of these spinning black holes? I mean, just to give people an idea, I mean, the thing is like literally spinning. I mean, it's got hundreds of millions of times, sometimes millions of times the mass of the sun, and yet it's rotating at ridiculous relativistic speeds, right?
It's strong magnetic fields. You have this intense X-ray radiation.
And so, like, what kind of impact do these things have on their home galaxies? Yeah,
so that's one of the big questions that we have right now is trying to understand how galaxies form and how black holes form over time. And it's a very active field, but right now we think that black holes, some material falls into the black hole, but stuff that doesn't fall in, some of it gets ejected out. Stuff that comes in close, it falls on these magnetic field lines, gets ejected out, and that puts a lot of energy into the galaxies. And there's current belief is that that energy can shut off star formation in a galaxy, can throw out the gas, ionize the gas. And so one of the big things NuSTAR is doing is finding black holes and watching that input that the black holes are putting into the galaxies.
I even remember that, like, if one, I'm trying to remember it, and I could be getting this wrong, but I remember, like, if one galaxy's, supermassive, actively feeding supermassive black hole is, quasaring towards some other galaxy, if they get close enough, they can actually sort of splash. These jets just go on for tremendous distances, right?
Yeah. Yeah. For radio galaxies, they're seen out to much larger than the size of the galaxy.
Wow, it's just sort of an extreme environment.
Yeah.
So we've got black holes, and so those are these places that are fairly, I guess, you know where they are. You can go back and observe them whenever you want. But a lot of the most kind of extreme X-ray events are very transitory, very quick. Gamma ray bursts, things like that. So do you get involved in those kinds of?
Yeah. We had a press release about 2 weeks ago, maybe 3 weeks ago, where it was actually a black hole event, but this black hole, Markarian 335, it's a black hole in a nearby galaxy, was seen to get brighter by another NASA satellite, the SWIFT satellite. And so NuSTAR did a target of opportunity that we were requested to watch this event, and we could watch with NuSTAR that this thing faded away after this big flare. And it was a group led out of Canada that wrote the paper, but they modeled what happened as this flare faded away, and they think that they're seeing material being ejected, not from the black hole itself, but from near the black hole, and it's moving away, and it moves towards you. It gets Doppler boosted, relativistically Doppler boosted, made to look brighter, and then you can also see some of it reflecting off of the accretion disk near the black hole. And we have a beautiful graphic that went out, and I think this press release went out pretty widely.
So what is the difference? I mean, I think a lot of people are familiar with telescopes like Swift. I mean, it's designed to go and catch those gamma ray bursts right after they happen and then watch the afterglow. But it's, I'd love to know sort of the difference in sort of what the capabilities of the instruments are.
Yeah. So NuSTAR, so Swift has a couple of different instruments on board. It has one that's doing a wide field monitoring of a lot of the sky, looking for these transient events, and then it has a smaller telescope for focusing lower energy X-ray light for following up these transient events. NuSTAR typically will go and look at something for a couple of hours to a couple of days. Sometimes we're looking at things that are known for years, like the sun, and sometimes we're reacting to these big events.
So I got a couple of questions have come in, and this one comes from Nancy Graziano, who is, of course, our producer and helped set up this interview in the first place. And Nancy wants to know, what is the life expectancy for NuSTAR hardware-wise, and is there a successor X-ray telescope planned?
So there are no consumables on NuSTAR. So our main mission lifetime will be the orbit slowly decays over time. I forget, we fall like a kilometer a year. And so we're expecting to get about another 10 years out of the orbit, and then hopefully nothing breaks, but that's the other big concern.
Right. Well, the thing that we always wonder about here at the Weekly Space Hangout is, did you install enough gyros on it?
Hopefully.
Because literally, Kepler and Hubble and a lot of these missions, they go because their gyros failed, and it's a perfectly good spacecraft. And then they come up with some kind of black magic science to actually make the spacecraft point after the gyros go down. So hoist the solar sail, and then you can turn it. But that's great. So really, there are no consumables. So I know, like, originally the mission was only a couple of years.
Yeah, these are always designed to last a certain amount of time. So we were built to last 2 years. We had our 2-year mission. If everything broke now, hopefully it doesn't. We had a very successful mission, but we're hoping for another decade.
And is there, as Nancy's second part of her question, is there a sort of large successor, like a good another X-ray observatory plan down the road?
Yeah, well, India just launched their first big X-ray mission about a month or two ago called AstroSat. Um, the Japanese in January are planning to launch a fairly large mission as well called Astro-H. And Astro-H will be the second instrument in orbit which does this focusing of high-energy X-ray light, though it also has a bunch of other cameras which are even more unique. It'll be the first high-resolution X-ray spectrometer in orbit, which is, people are very excited about that. And then Europe has recently decided that I think it's going to be the L2, their next large sort of flagship class mission is something called Athena, which will be a $1 billion plus mission to study high energy X-rays.
There are, I remember there are plans for an Event Horizon mission as well, isn't there?
I think
one that would actually be able to resolve the event horizon around supermassive black holes.
Yeah, people talk about the Event Horizon telescope, but that's more of a array of radio dishes on the ground. Yeah.
Right. So not X-rays.
Yeah.
Yeah. Yeah. It'd be great. It'd be amazing to be able to resolve that. This question comes from Eamon Fanton. Can NuSTAR distinguish between black holes, neutron stars, and quasars? How do you do this at extreme distances when everything looks like a point source?
Yeah, so one of our big results was, so there's a population of bright X-ray sources that we see in nearby galaxies. They're called ultra-luminous X-ray sources, something that people have been seeing for more than a decade. And often when you look at a nearby galaxy, the brightest X-ray source is something in the disk of the galaxy, not at the center. We think that every galaxy has a big black hole in the center, so you're not surprised when you see a big X-ray source in the center. But these bright X-ray sources in the disk of the galaxies have been confusing because they're too bright to be a normal black hole formed from an exploding star like a supernova, where it can create a black hole weighing 10 or tens of times as much as the sun. They're too bright to be a normally accreting stellar mass black hole, and so people thought maybe they're hyper accretion onto a normal black hole, or maybe they're really big black holes weighing 1,000 or 10,000 times as much as the sun. So something in between what gets created by a supernova, but not as big as what's in the center of a galaxy that can weigh 100 million times as much as the sun. And so NuSTAR has had a program studying these ultraluminous X-ray sources, and we had a big result earlier this year, maybe the end of last year, where we saw pulsations from one of these. So it was flickering in the X-rays, I think at a cadence of a couple of seconds, 7 seconds or something. And basically that was a big surprise because black holes shouldn't flicker. They shouldn't have a regular period. They don't have any edge to them. You don't get that. Neutron stars can have that, like a pulsar where you have something rotating and it comes in and out of your line of sight. And so
right, but nothing's getting off a black hole to, just the accretion disk.
Right, and then the accretion disk, you can't get a pulsation from it. And so it was a real big surprise that this ultraluminous X-ray source in M82, the Cigar Galaxy, was pulsating, which meant it had to be a neutron star. And the neutron stars, can't get larger than a couple of times the mass of the sun. So this thing was 20 times more luminous than any other neutron star known. It has to be accreting at this unstably high rate, like it's gorging on material, shooting out tons of photons, and so we can't image them. It's still a point source, but the time domain information let us distinguish a neutron star from a black hole.
But something that's guzzling material that quickly, it could turn into a black hole if it crosses some
threshold.
Limit, right? Yeah, it might be an object worthy of further study. I'm sure. Yeah. I'm sure you're gonna come back and take a peek every now and then. Richard Gustafsson asks, is the black hole's rotation related to the galaxy's rotation? So is there any connection between how fast the black hole is rotating and how fast the galaxy is rotating?
That's a good question. Probably not.
Okay, well, if you do write the paper, Rickard, just give him give him a credit. Okay, cool. Do we know which came first yet, the supermassive black hole or the galaxy that surrounds it?
We don't know. We don't know. One of the big problems is maybe if you talked about this on previous hangouts that we're finding black holes within a first billion years after the Big Bang with surprisingly large masses, and theorists are really having a hard time getting something that big that quickly to form. So there's some thoughts that maybe you have primordial black holes, or maybe the first generation of stars are really extreme and they create these big black holes.
Right. I mean, this is the reason why we get those accretion disks in the first place, right? Is that it's like I always liken it to like a bathtub drain, right? There's only so much water that can get down the bathtub drain, then the bathtub fills up, and you can see it all just sort of slowly turning around. And with black holes, it's this same kind of thing. And yet, strangely, they have way too much mass too early. And like, just back to your paperwork, theorists.
Maybe merging, maybe those first generation black holes can get very big. That's sort of the preferred theory today. Maybe it will change in 2 years.
Oh, I see. So they could accrete their mass separately, and then you could mash these two things together, and that's a way that they could feed or gain in size more quickly.
Yeah.
Oh, that makes sense. Okay. This question comes from Alexander Howlett. Has your mission been studying Sagittarius A recently? And of course, that's the supermassive black hole at the heart of the Milky Way.
Yeah, we've done a fair number of studies of Sag A star. We've caught a couple of flares from it. There was an event where I guess it was in 2013, suddenly something near Sag A star got very, very bright and kind of hid Sag A star a bit. And NuSTAR was one of the first on to watch this big flaring event. And again, we saw pulsations from it, and we were the first people to see pulsations from this flaring thing that told us it had to be a neutron star near Sag A star. And so we have been monitoring Sag A star. We often do it in working with other telescopes, both on the ground and in space, and we intend to continue doing that.
There was like a blob of like gas. It was thought to be maybe gas, and maybe it was a star that got consumed just in the last year or so.
Yeah, the G2 complex, I believe it was called. Yeah, so there was this expectation that suddenly Sag A star was going to get immensely brighter, and that didn't really happen. But I think, I don't really work on Sag A star so much, but I think we think that event is largely over, and it didn't get as bright as some theorists thought it might get.
Quick note from Carolyn B. I had a talk at my local Astro Society about X-ray telescopes, and they were compared to lobsters' eyes. So have you heard that comparison?
Not our telescope. Ours is a different design, but there are some X-ray telescopes that follow a lobster eye design, and some future plans for very wide areas, so you get to image a lot of the sky at once with this sort of lobster eye design. Yeah.
Okay, I got one last question, and then I think we'll let you go. So this question comes from Adam Synergy. What's the status of intermediate-sized black holes, and why are they so difficult to find, observe, and characterize?
Great question, and one that we can't fully answer still right now. There are a handful, and by a handful, it's like a Simpson's hand, not a human hand. So, maybe one or two or three pretty well-established intermediate mass black holes out there. It seems like there should be a lot more, because we see these small ones, we see these big ones. There has to be something in between. I think we're still trying to find them. I think they tend to be in the nuclei of small galaxies, and there's a lot of work going on that front. A lot of papers coming out, every couple of months on that. There's been searches for them in globular clusters as well, and those tend to not find intermediate mass black holes in them. And so
which is surprising, because they're so densely populated with stars, and you would possibly expect those black holes to collide with each other.
Yeah.
Yeah.
They form a bit differently than galaxies, so maybe it's not surprising. Yeah.
So I'd love to hear sort of what the future holds. What are sort of some of the big, if you had your checklist when you started the mission of all of the kinds of scientific discoveries that you're hoping to sort of shed some light on, is there anything that's left on your list?
Yeah, we we're doing a whole range of studies trying to understand the regions around black holes better, and that's exciting. And we're making progress on that, and that's great. We've been studying supernova explosions, and that's work that's continuing. But it's one of the main designs for the mission was to study supernovae. There's some mysteries about how stars explode that we're helping to understand. And one of the big things that is on our checklist that hasn't happened yet is we would love a very nearby supernova to go off while NuSTAR is in orbit. And there's some very distinct predictions from the theorists of things that you would catch very early on. And they depend from theory to theory, so they are a good diagnostic of the physics of the explosion. So on my checklist would be big supernova go off in the local group or in the galaxy in the next 2 years.
Like 1987A, like something of that kind of event?
Yeah, that would be fabulous.
I mean, isn't there thought to be like 1 or 2 a year, but we just can't necessarily see them?
No, I think it's about 1 per 25 years per galaxy.
Oh, okay, right. Yeah. So we're due.
We're due.
It's time. It's our time. Yeah. Great. Well, Daniel, thank you so much for joining us this week. If people want to find out more about the mission or follow you, where can they find out more?
We have a website, nustar.caltech.edu. Gives a lot of information about the mission. We have a Twitter feed and and people are welcome to email me as well. Daniel.k.stern@jpl.nasa.gov.
Whoa. Okay. I wouldn't have made that offer, but here it comes. Okay, great. Well, thank you again for joining us. Thanks a lot for sort of updating us on the X-ray observations. It's really exciting stuff, and let us know when you see that supernova.
Okay, thank you.
All right, thanks a lot.
Bye.
Okay, well, let's move on to the rest of the stuff. So. Let's give Morgan and Sandy one item, and then Kimberly, you can reach parity, and then we'll try and sort of do this handoff until you run out of stories, and then they just keep rolling. So, Morgan, Sandy, let's go with the big piece of news.
Well, the biggest news, as it has been for the last 6 months or so, of course, was Pluto. The meetings like the DPS are often coming out parties for the first scientific results to come out of these big missions. And we've been watching sort of the pretty press images and some of the first hints of what's going on trickle out sort of week after week for the last 5 or so months. But here at DPS, we had basically 2 straight days of nothing but Pluto results. And it started Monday morning at 8:30 a.m. and just continued right on through the day. And there's far too many Pluto results to actually sort of comprehensively talk about in the next 30 minutes. And so the one I want to highlight actually isn't a result for Pluto at all, but a result about Pluto's moons. The most recent results we've been getting over the last month or so have been about these smaller moons of Pluto. We know about Pluto and we know about Charon, and the great pictures that have been taken of those. But recently, a lot more of the data has been coming down, and it's included a lot of pictures and other observations of the smaller moons. And Mark Showalter of the SETI Institute out in California brought some very surprising news to the meeting this week, and that's that pretty much all of Pluto's smaller moons, that's Nix, Styx, Hydra, and Kerberos, they're all not. They shouldn't be able to exist in the way that they do.
It's not chaos, it's pandemonium.
And this is sort of led off by the farthest and largest of these moons, Hydra, which seems to be spinning almost impossibly fast. Every time a moon goes around a planet, it's also rotating about its rotational axis. And for our moon, our moon makes 1 rotation for every orbit.
Right,
the smaller
tidally
moons
locked
of Pluto,
to the Earth.
It's tidally locked, that's right. The smaller moons of Pluto, which you'd also expect to be tidally locked, are not. They're rotating 5 to 10 times for every 1 orbit around Pluto that they make. But Hydra, which is farthest out and ought to be rotating most slowly, rotates 89 times for every 1 orbit it goes around Pluto. And this is about the appropriate rotation speed if this was a free Kuiper belt object out floating through empty space. But there should be basically no physical mechanism that enables a moon to spin at a speed like that. And Showalter and colleagues really don't have an explanation for what might be causing this to happen. Another one of Pluto's moons, Nex, was spinning at one speed when they observed it earlier in the New Horizons mission, and when they arrived at the New Horizons, or at Pluto, they found that it was spinning at an entirely different speed.
What? And
they're very sure about both of these measurements, and they don't see a mechanism to sort of go from one to the other. It also turns out that pretty much all of these small moons of Pluto are rotating along axes that are in no way aligned with the rotational axis of Pluto. And that's surprising because all the evidence that we have otherwise suggests that the moons of Pluto likely formed in the Pluto system. But if that were to happen, you would expect the axis along which Pluto rotates and the moons orbit about to be the same axis that the moons rotate about. We see this at Jupiter, we see this at Saturn, we see this for Earth's moon. That doesn't seem to be the case at all for Pluto. And so taken together, all of these results really tell us that in some ways we know less about how the Pluto satellite system worked than we did before New Horizons got there.
What, you mean like when we were just making things up?
Yeah, I mean, and I was
making assumptions, making incorrect assumptions, and now.
Yeah, I was talking with Mark Showalter about this on Wednesday, and he joked to me that if he had published these results, his journal article never would have been accepted, because these seem to deviate so strongly from any accepted understanding of how satellite systems work that we really need to sort of start over from square one to understand what could be going on in this system.
Okay, so now I know you said they have no idea what's going on, but come on, I would have just been, asking again and again and again to hear some ideas. Like,
right. So there are some
how do you get? So let's take the weirder one, right? How do you get an object to rotate at different rates over the course of a few months?
So that's maybe even the more challenging of the two to explain. And in planetary science, we typically use the same explanation for everything that we don't understand, and that's that a big rock came out of nowhere and hit it.
Yeah.
And
it works for every planetary body in the solar system.
The problem here is that New Horizons has been staring at the Pluto system for year after year after year. If there had been a collision sufficient to knock this sort of off kilter, we ought to have seen debris from that. And they were looking exceptionally hard for debris because they were afraid of running into it. And no such debris has been seen, and that makes it difficult to imagine that a collision could have occurred and gone unnoticed.
I'm not saying it's aliens.
Yeah, for sure. Oh, don't get us started on that, Sonny. So, Sonny, what explanation do you like the best?
Well, I was not. I don't think I was in that session actually. I was in an asteroid session at that point. So I was listening to cool asteroid results. You'll have to ask Morgan the dynamic system.
Yeah. So so there's one thing that's absolutely unique about the Pluto system in comparison to all other planetary systems in the solar system, and that's that it's a binary. Pluto and Charon orbit relatively close to each other, and they're relatively similar in size. And we don't see that anywhere else in the solar system. The next closest thing would be Earth and Moon, and the Moon is much, much smaller compared to the Earth, and Charon is compared to Pluto. And so probably this binary configuration is leading to some extremely turbulent gravitational forces being exerted on these various moons. And without a very precise knowledge of the sort of status of the Charon-Pluto system in terms of their composition, their velocity, their orientation, it's difficult to impossible to predict what effects that might have on these other bodies.
I see. So you've kind of got, the barycenter of the two objects is actually outside of Pluto, and so the two are kind of doing this.
Right,
and
exactly.
That motion would then cause the rest of the system to act a little wonky. Okay.
That's a hypothesis, and it's probably better than any other hypothesis we have right now. And now that we have all this data, dynamicists will be able to go back and try to recreate the situation and see if they can simulate or calculate what might have happened. But right now, from observation alone, we have very little understanding of of how this sort of system might have been able to transpire.
That's that's pretty cool. All right, well, let's move back. We'll go back to Kimberly now. We'll talk to Kimberly a bit, and then we'll come back and hear what's happening with asteroids. Kimberly, just a warning. Some people mentioned that you're very quiet, so you're going to have to yell.
How about now? Is that better?
You're definitely quiet, but go ahead and let's talk about a twin Venus.
Right. So there was a very exciting exoplanet discovery that happened. That was released yesterday or the day before. It is a really nearby exoplanet, only a few parsecs away, and 39 light years, and it is called GJ1132b, and it is so exciting, not just because it's really close and it's around a sun-like star, but it is also very Earth-like in that it is only about 20% larger than the Earth and only about 60% more massive. So we know, because we have mass and we have size, that it is a rocky planet around a sun-like star very nearby. Unfortunately, it is not in the habitable zone, which would sort of be the trifecta of awesome planet discovery.
That would be Earth 2.0.
That would be Earth 2.0. It's a little bit too close to its star in order to be habitable, which is why we call it a Venus twin instead.
But Venus is Earth's evil twin.
Yeah.
So if you have Venus's evil twin, does that make it good again? I don't know.
Or more evil?
More evil? Yeah, extra evil. This is like a really evil planet.
Sure there's some sort of pyramid of evilness versus
right.
Not black or white. But the surface temperature of this planet has been described sort of about as hot as your oven will go, about 450 degrees Fahrenheit or so, which is too hot for water, but it could still be massive enough and cool enough to actually retain an atmosphere, which is also why we're very, very excited about this, because it's close enough that in a few years James Webb will be able to look at it. It's the exact type of target that James Webb is looking for in order to study the atmospheres of small Earth-like planets.
Which technique turned up this? Was this another of the transit method?
Yeah, it was discovered by the M-Earth project, which is run out of MIT. It's a series of robotic telescopes that's actually down in Chile, and it uses the transit method to detect it. And then it was also followed up with radial velocity, which is how we got mass.
That is awesome.
Very
cool.
Exciting discovery.
Awesome. Okay, back to Morgan and Sandy. Let's have another piece of news. I want to hear something from Sandy this time.
All right, well, there's been some asteroid stuff, and there's also some comet stuff going on at this meeting, including results from Rosetta, the European space probe at Comet Churyumov-Gerasimenko. They're a little annoyed at their Philae lander. It doesn't write, it doesn't call, but that doesn't mean that the Rosetta spacecraft isn't doing science. One of the more interesting results is that they're finding the comet is actually getting lighter in color as it gets closer to the sun, and that means that the material that's coming out on the surface of the comet from inside the comet is fresher and it's lighter in color. So the albedo is changing, so the whole comet is getting brighter, which is kind of cool. And then at one of the asteroid sessions, they actually kicked off with one of the people who came up with sort of one of the concepts we have about how asteroids change how they spin. And so most of the time when we think about objects in space, we think about how they're affected by gravitational forces, whether it's resonances or gravitational attraction to other bodies. But with asteroids, they're about the right size, and a lot of them are asymmetrical, so they can be affected by photons, by thermal torques as sunlight hits these asteroids and they re-emit heat. And this is something that we call YORP. It's named after Yarkovsky, O'Keefe, Ratajkowski, and Paddock. And so this Paddock fellow was at the meeting, and he was talking about how he came up with this concept for YORP, about how he would sit at the bottom of a swimming pool with rocks and watch them spin, and how he did experiments in the lab, and how his colleague Rubenkam came up with the name of YORP after watching too much of the Muppet Show with the Muppet named York. My license plate says YORP, so I was really stoked to meet these guys who came up with this concept, and he loves the fact that I have a license plate called YORP.
So this is this idea that the asteroids act like solar sails, right? And that
not quite like solar sails. That's radiation pressure. So this is a different effect. So it causes the asteroids to heat up when the sunlight shines on them, but because they're asymmetric, they re-radiate heat asymmetrically, and that gives these bodies a bit of a thermal torque, so it'll change not only how fast they spin, but what direction they're pointing in.
So it's almost like they've got retro thrusters on them that changes
and there's,
their
some
spin rate.
insinuation that you could, paint half of an asteroid white and let these thermal forces move an asteroid out of the way if it was on a collision course with Earth and you had enough warning.
Like 100 million years or something.
Yeah, this is not the fastest thing, but you actually do see asteroids spinning up due to Yorp, and you see them changing their orbits due to the Yarkovsky effect over human lifetimes, which is kind of cool. And we've actually measured it for, we've modeled it for bodies like Bennu that will be visited by OSIRIS-REx in the coming years.
One of the things that I saw, ESA released a video this week to kind of coincide with the announcement they made at the conference, and they had a really great animation of how they think 67P formed. I don't know if you got a chance to see. It was sort of, that it got, possibly some kind of collision or something that sort of tore it apart and sort of mashed it together like a duck.
Yeah, there's some interesting insinuations there, but from the asteroid community, we see a lot of these sort of contact binary objects. We see a lot of asteroids stuck together. And a couple days ago, one of my colleagues, Michael Bush, his student Kaylee Brower, she presented a poster on the shape model of an asteroid that looks a lot like Comet Churyumov-Gerasimenko, but instead of being made of ice, it's made of rocky stuff. It's made of silicates, just ye old-fashioned rocks. So it's interesting that we see this sort of duck shape, this contact binary shape, across the solar system. We see it in comets, we see it in asteroids. So maybe there's something else at work there. So maybe there's something like that the sunshine, that you could have like a sublimation Yorp effect, that sunlight causes, sunlight combined with sublimation of these ices on comets can cause these bodies to spin up and not only change which direction they're pointing in or how fast they're spinning, but actually change the shape of these objects.
Can they spin up fast enough to sort of tear themselves apart?
Yes, actually. And so a lot of asteroids that we see have these sort of equatorial ridges. They look like tops. And we think that these bodies spin up fast enough that the material at their equators spins off, forms these ridges, and that sometimes it can even form moons around asteroids. We see that about 16% of asteroids over 200 meters have moons, and we think that's mostly due to Yorp spin-up.
So the Yorp spins them up, they flatten out like a pancake, spin out debris, and then the Yorp, say, slows them down again, and some of the stuff sort of accretes back on them and gives them this ridge again, and they're left with moons?
Well, actually what's happening, because these bodies don't have a lot of strength, and because they're spinning close to their breakup rate, is that the gravitational acceleration of material at their equators is negligible. It's just the material could just be lofted at these ridges, which is kind of cool.
Yeah.
So now we have all these flavors of Yorp. We have binary Yorp, we have sublimation Yorp, S Yorp, we have tangential Yorp, T Yorp.
Right. It's just new initials for the people who are involved in the discovery. All right, Kimberly, we're going to talk to you about what the new definition of planet.
Sure. First, I want to say that I love the fact that we said Yorp so many times. That was super fun. It's one of my favorite acronyms, just because it's a fun word. But yes, there is a new definition of a planet that someone has proposed. I believe it was actually at the DPS meeting as well, so more DPS results. But this one actually has to do with exoplanets. I'm sure many of you remember a few years ago when the International Astronomical Union actually defined a planet, and that was when Pluto was ceremoniously kicked out of the Planet Club. The three criteria that they used was that it had to be in orbit around the sun, it had to be massive enough to be a sphere, and it had to have cleared its orbit of debris. And the third one of those is why Pluto was no longer a planet. But the problem with that definition is that for every single exoplanet that we know, there's absolutely no way we can tell whether or not it has cleared its orbit, and there's no way we can define the 1,900 exoplanets that we've confirmed. We can't actually define them as planets, and that is a problem. And so Jean-Luc Margot, who's over at UCLA, came up with a mathematical way to determine sort of probabilistically whether or not a planet of a certain mass would have been able to clear its orbit of any debris given enough time. And so he created this mathematical model that only requires us to know what the star's mass is, what the planet's mass is, and how old the system is. and applied this to not only the planets in our solar system and was able to recover the exact same results that IAU was hoping for. That is that we have 8 planets and then we have a bunch of dwarf planets that aren't planets. And then also applied it to all of the exoplanets that we know, and luckily all of those exoplanets passed the test. But that's not such a surprising result because right now our detection methods are very biased towards the most massive planets. So hopefully all of those will be able to sweep everything away if something as small as Mars can do it.
But no hope for Pluto. This didn't.
No hope for Pluto.
No, they weren't able to sort of redefine Pluto back into planethood.
No, but the funny thing about this as well, I just actually learned today, is that under this new definition, the moon would actually be defined as a planet, which is strange. But part of this definition is that if you have a binary planet system, sort of like either Pluto-Charon or Earth-Moon, even, if they're both in the same orbit and have cleared that orbit, they're both planets. So we would define the moon as a planet under this new system if it occurred in an extrasolar system. But so it's still in the works. It's being proposed, and hopefully in the next few years, at the next IAU meeting, it'll have been tweaked enough so that we don't accidentally define the moon as a planet.
Oops. All right, so I'm going to now go back to Morgan and Sandy. So everyone who cranked their volume to listen to Kimberly, you're now going to need to turn it back down, or it's going to wreck your eardrums here. Morgan, what's the next big piece of news from the meeting?
Well, probably the most well-received presentation that we saw this week at the DPS actually wasn't a scientific result. It was a result.
It was a scientific
result. It was a result about scientists.
A scientist result.
Totally an institutional review board and sociologists on it.
So what this study aimed to do was understand the climate in which we all do our science. And so it was a voluntary survey administered to American astronomers that asked questions about people's race and their religion and their marital status, their disability status, etc., and then whether or not they had positive experiences, negative experiences with these various traits in their workplace, at conferences, when publishing papers, etc. And in the wake of the incident that we've discussed in the past at the University of California at Berkeley, the talk this week focused mainly on the effects of one's gender, on how sort of inviting one's workplace was. And unfortunately, but unsurprisingly, it turns out that gender plays a pretty strong role in whether or not your workplace is an inviting place to be. And of the more than 400 respondents to this survey, and this is still preliminary work, 60% of those said that they had felt verbally assaulted based upon their gender, and 10% said that they felt physically assaulted based on their gender. And this launched a sort of broader and ongoing conversation within the conference about how we here at the DPS can better handle issues as they arrive and create a more inviting climate for scientists of all ages and all various other things, as well as what we can do across our home institutions and astronomy in general to try to get rid of as much of this as possible, as quickly as possible, because the effects that were revealed within this survey show that a large number of respondents, for example, were declining to join prestigious missions and things like that because they felt that this would place them in an unsafe situation. And when people are actively going out of the way to hurt their own careers simply to avoid being physically hurt themselves, then we know that we have a substantial problem that needs immediate solution. And so hopefully going forward, as these results are published in a number of papers that should be coming up in the coming year, we'll be able to apply the lessons learned from this to make, as much as possible, our environments welcoming for everyone.
Did they have any concrete solutions, or are they still just, like at this point, just gathering the data?
yes, they're coming up with solutions, but it's mostly that the emphasis has been that senior people really need to step up. That they and I need to sit up because I'm a foot shorter than Morgan. That the senior people in our field really need to step up. They need to set expectations for what good behavior is. They need to call out bad behavior as they see it, and that they really do need to make the workplace a welcoming environment where one can actually do work. And in the United States, you are entitled to a safe workplace free of discrimination and free from harassment. There are actually laws about that cover.
Yeah, these laws have been figured out a long time ago.
I think, so Kimberly was asking about whether it was remarked about for results for undergrads, grads, and faculty and staff. They did, I think, break that up, but they found that people had been, the results did break that down, I think, but it found that mostly people had been, had experienced harassment from senior people, and I think that's mostly what the results focus on, that people have experienced this degree of harassment at pretty much every stage in their career. But I think there are solutions, and there are ways for sort of these problems to get solved, and I think it's time for senior people in the field and people in leadership positions, and even outside of astronomy, to say enough is enough. We're going to change things about our workplace environments.
Well, we'll be looking forward to seeing what I guess what the results are and what, if any significant changes are made. And I know, as we did a whole sort of almost an entire show about this like about a month back. Hopefully you guys, as people who are actually in the community, can report on whether or not things are changing in the right direction.
In 10 years, Fraser. Some other fun stuff from the meeting was that on the first day that there's insinuation that there are ice volcanoes on Pluto, which is kind of cool because people have been wanting there to be ice volcanoes in other parts of the solar system for pretty much as long as they've been looking at other planetary bodies. So the volcanologists are trying to figure out how to make this work, but I think they're it's a possibility that there are ice volcanoes, and that's pretty cool.
We saw a picture of Morgan with some cryovolcanoes on Enceladus.
Right. Yeah. There are a lot of photos of people with the.
Yeah, they had this big sort of meter across model of the active regions on Enceladus, and it was maybe the most popular photo posing location in the entire meeting.
There's a photo of Emily Lakdawalla and Alex Parker and I with it, which was a lot of fun. The other cool thing, which is sort of one of the final results that I thought was neat, was that we're actually seeing the effects of meteor streams on the planet Mercury, that we're actually seeing the bits from the comet Encke hitting Mercury. So we're seeing really just kind of fun, active processes all throughout the solar system. Not maybe so active on Pluto these days, but I guess you're seeing the various frost, you're seeing ices on Pluto. That there's really, we don't live in sort of this cold, dead solar system. There's all sorts of stuff happening, whether you're close to the sun or whether you're far away from the sun. And there's a lot of sort of unexpected stuff at Pluto, and I think the results from Pluto are going to keep coming in, and they're going to keep being amazing.
Like we no longer understand how moons orbit and rotate. That was important. Yeah, weird.
Gravity is hard. Let's go resonance.
Yeah. Morgan, any other stories that caught your eye?
Morgan had a really nice result about Saturn's rings, and everyone tells me he did a really nice talk. So.
Saturn's rings still kind of work how we think they would, so they're not quite as crazy as Pluto.
What was the result? Come on, let's hear it. What was the result, Morgan?
Also, the result that we talked about this week was that Saturn actually has a unique configuration of moons in which it has two moons that share the same orbit, named Janus and Epimetheus. And every 4 years exactly, on January 21st, they swap positions. One becomes closer to Saturn, the other gets farther apart. And within the rings of Saturn, the gravity from these moons excites waves that then travel throughout the rings. And you can imagine that when these moons swap, they're going to stir up the rings with their gravity as that happens. And what we've been tracking from 2006 through 2010, and we're now starting to see it again in 2014, is that when one of these configuration changes happens, it launches a giant pulse that travels at all longitudes around the rings out much faster than the normal waves. And so you can kind of think of this as a tidal bore coming in, for example, in the Bay of Fundy, as opposed to just your normal tide coming in and out. And those can travel much faster than the actual water waves we see in the ocean themselves. And the hope is that ultimately we might be able to see a similar sort of phenomenon going on in the disks around forming stars. Because, as Kimberly has told us in the past, we think that as planets form, they migrate. And these migrating planets might look very similar to the migrating moons that we see at Saturn. And hopefully their effects would be just as visible on the protoplanetary disks.
Super interesting. So if you're on one of those moons, would you never see the other one?
So most of the time they do indeed spend about 180 degrees apart from one another, but they actually do drift within 5 or 6 degrees right before they make the swap. But these are very small objects, and so whether you could see them with the unaided eye, I'm not sure, but with a small telescope while standing on one, there would definitely be periods of time in which you could see the other.
Poking out the other side. Cool. Okay. Well, we've reached sort of the end of our hour, so why don't we wrap things up? Now, Kimberly and Sandy. Actually, Kimberly, where can people find out more about what you're doing?
You can follow me on Twitter after you turn up your speakers to actually hear me talking.
Astro Kim Cartier.
Yes. I also have a website, kimberlycartier.org, and Google Plus, of course. And if you're going to be in the New Jersey area tomorrow, Morgan and I will be giving presentations at the New Jersey Astronomical Association's Space and Astronomy Day in the early afternoon, so come and say hello in person.
So where do they go?
The event is in Glen Gardner, New Jersey, which is sort of the northwest-ish corner of New Jersey. So it's not too far of a drive from many of the major cities, Pennsylvania, New Jersey, New York, and that whole area.
Great. And you guys are going to be there in the same room talking about, or you're going to, what are your presentations on?
Life, the universe, and everything.
Perfect.
I cover everything.
Great. Morgan, and what were you going to talk about?
Indeed. So I'm going to share a couple of cute slides from mine in case you'd like to see a picture of this cute frog. And I will be talking about the search for life out there in the galaxy and in the universe, and how we might interpret our place in the cosmos in terms of the search for life around other stars.
That's awesome. Have you solved the Fermi paradox?
Well, you'll have to come tomorrow afternoon and find out.
Well, I hope someone records it, because I live on Vancouver Island, which is very far away.
I think that there will, in fact, be a recording.
Okay, great. But if say a person wasn't there to see this in person, where can they find out more about you?
Oh, well, I recommend that you follow me on Twitter, at Morgan Rehnberg. You can see all of my thoughts, sometimes more serious than not, about the meeting over the last week, or you can check out some of my latest work over at morganrenberg.com.
Sandy, where do people find out
You
more?
can find me at sandy.com, or you can find me on Twitter as Sandy.
We make it simple here.
So
You really
simple.
have no excuse not to.
How are you guys doing? You're at the end of the conference now, right?
Oh
It's
my
done?
God, I'm falling asleep.
It's zombie status.
I was
Yeah,
at 1:20 in the morning talking with one of Morgan's collaborators about.
Yeah. It is an exhausting process, not just the sort of getting up super early, attending all of the stuff during the day, but also astronomers tend to cut loose in the evenings as well, and you have to keep up with them.
They're much better behaved than the American Astronomical Society. We don't have wild parties.
Okay, because that place is a zoo. All
Although
right.
there may be some Twitter-based evidence that wasn't always the
I
case
think
during
Right.
during this conference.
We took a lot of selfies. It's DPS, I think, is one of my favorite weeks of the year. So it's really good to see people, and you don't really want to go back and
It's
get
like a
sleep.
big family
It's
reunion.
like a family reunion.
Yeah, totally. They're a hoot. Okay, great. And of course, I'm FKN on Twitter. And if you haven't already, subscribe to this YouTube channel and see all of the cool episodes that we're releasing. We just released the episode on the Guide to Space about why we don't see eclipses every month. So if you wanted to know, there's your answer. All right. Well, thanks everyone for watching. Thanks to everyone for on the panel, as well as our special guest, Daniel Stern. Thanks to Nancy and the rest of the WSH crew for helping to organize and coordinate. We couldn't do the show without you. If you want to join this amazing community, go to WSHcrew-net. Maybe it's .org. Oh, I get this wrong every week.
WSH-crew.net.
.net. I got it right. Okay.
.net is that's not going to get you anywhere.
That'll get you sad.
Yeah. .net. So WSH-crew.net.
Just Google it.
Yeah, just Google it, and also you can find the Google Plus community. And they are really the heart and soul behind the show. They are coordinating some of the stories we talk about. They are organizing the guests. And if you want to be a part of this, if you want to not just enjoy a show, but actually be involved in its creation, then this is the community for you. All right. Well, thanks, everyone. We will see you all next week.
Thanks, Fraser.
Bye.